Hi, I'm Connor Labonte,
And I'm Colin Melville.
and this is our technical presentation for the Chain of Responsibility design pattern.
So you may be asking yourself, what is a chain of responsibility? Well, a chain of responsibility is a design pattern which allows you to separate out the implementation and the steps of a process into separate handlers so that a request will happen and that request will then go through every single handler and will determine whether or not it needs to fulfill it, or maybe it just needs to say, this actually is not something I can work on, so I can pass it on to the next handler. So you might be asking, what are some use cases of this? Well, say you're trying to set up an online store. And you sit there and you're like, I want a really secure store. So every single time someone orders, they have to go through user authentication. So you sit down and you code up the best user authentication you can think of. But there's some problems with your authentication. So maybe it is the fact that you find out that you're vulnerable to brute force hits. So in order to get around that, what you do is you sit down and you figure out how many requests you get from certain IPs, or you sit down and you figure out how many requests a certain user has for logins and how many of them fail. So if they have a certain number of failed requests over and over again, then you sit down and say, hey, actually, they don't get to give you a pass on. And if this happens, then what will happen is it will ban the IP and it will stop the request from filling down that chain. So you implement that and you hack that all together, but it's a huge feature and you didn't originally plan on it, so you kind of have to work around the code you already have. But then all this extra code is making it really slow for your authentication to respond. So in order to make it speed up a little faster, you say, well, okay, if the user really hasn't had anything change on their end, then I don't really have to recheck if they need to log in, right? I mean, if it's within a few minutes of itself, I don't really need to keep doing it. And so I can just cache it, right? So every couple of minutes, it might reset that cache, or maybe it's a certain cooldown for every user, where if they're accessing from the exact same IP under the exact same circumstances, and the same computer and everything, then you'll just accept it again. Well, so you go and you put this code together, and it works great. It's amazing. But then later down the line, another feature comes along. Small problem is the fact that you've made all this code and it's really messy though. And you sit there and you're trying to add this new feature in and you just can't get it to work and you think you have to rewrite it all and it's just not going to work very well. Well, this is where chain of responsibilities come in. So by breaking down each of those processes into its own step, which handles the request separately, it actually makes much cleaner code.
The main participants in the Chain of Responsibility design pattern are the client, which sends the request, and each specific handler in the chain. While the client has access to all the handlers, each handler in the chain only knows what the next handler in the chain is. This link structure makes this design pattern very similar to a singly linked list, which is shown below. Once the chain is linked, the request is sent to the head of the chain, which will then pass the request through each successive handler until the request is fulfilled. One important thing we should be able to handle is the request making it to the end of the chain, so there should always be code in place to make sure that the last handler in the chain doesn't try to pass on the request to a non-existent handler.
So here we have a UML diagram. With this UML diagram, on the left-hand side, we have the class diagram. So in this case, we have some abstract handler or some interface, which is like defines the way that every handler should interact with each other. And then on the below that, we actually have the concrete handler, which inherits from this abstract one. So this is the actual implementation of it. Now, this might be something like the thing that handles the caching response, or maybe it checks the database to make sure they actually logged in correctly, or maybe it handles if they've had a lot of requests over again. And so if we look on the right, we actually have our serial diagram. So that serial diagram, the request, and it goes into the first handler, and the handler does its own internal processes on it. So again, say this is like the caching system, where it's like, okay, this thing has had no changes to the request, so I can actually just fulfill it again without thinking about it. Or maybe it fails and you pass and you go on to the second one. And you create the second part of the request. And maybe it's actually the part that handles the whether or not there's been a lot of bad requests from them. So usually a user probably won't spam multiple requests very quickly unless they're doing something malicious. And so if they have a bunch of spammed requests, you might say actually put them on a timeout kind of system, cool them down until they can actually, we can verify if they're actually correct, or maybe there's just some weird thing happening on their end. And then the very last one would be the actual checking if the authentication actually goes through. So that's checking your database and going in and seeing if it works correctly. So some of the advantages to having some of the advantages to a chain of responsibility. So it reduces object coupling. So objects no longer have to really know a lot about each other to handle stuff. It actually just means that as long as they follow that interface, then all of that stuff will actually follow correctly because all it needs to do is handle its own part of the program, and it doesn't need to even know anything about the external parts of the program. In addition to that, we have it simplifies object implementation. You don't actually need to worry about the implementation details as a person who is just handling the request. You say first it goes into this chunk, then it goes to the next chunk, and then it goes to the last chunk. And you never even have to think about how it's actually implemented to get all those requests through, unlike with this monolithic authentication code you may have had before. It also allows for the sequence to change during runtime. So we no longer have to sit down and have a handler declared at compile time where we say, okay, first these handles are going to happen at compile time. You can actually change it in runtime because it works kind of like a linked list, as we talked about earlier. And then lastly, it follows the open and close principle. So what the open and close principle states is essentially that any object should be able to handle things entirely in terms of itself, and so there shouldn't be anything that can mess with it outside of it. And of course, these follow that in the sense that they only link between each other with requests. They don't actually modify each other in any way. So some of the disadvantages of chain of responsibility. So there's no guarantee that any handler in a chain will be able to fulfill the request, which means that there's no guarantee that the chain will be able to fulfill the request. Now, there are ways around this, because you could have something like a default handler at the end, which catches it if everything else fails, but that's actually very sloppy code. More often than not, you probably want to have something, you would have to explicitly check every single case, because if you just have some universal, like, except case, that's a very bad form. Another option, again, is the fact that very simple chains that don't have a lot of complexity to them will actually end up being unnecessary because maybe they're very static, so we don't ever change the order of them. Or maybe they're only ever used in one place, or there's only a couple of them, so they don't ever change that much. Well, then creating this full system might actually slow it down, or it might make it overly bloated, which makes it so that it wasn't entirely needed.
In order to implement the chain of responsibility design pattern, there are 3 steps to follow. First, a class should be created for each handler in the chain. These classes should all contain a next pointer, which will lead to the next object in the chain, and should be programmed to independently process the request and choose to send the request along the chain, fulfill the request, or both. There are many ways to achieve this, but the simplest way is to create an abstract handler class, which contains the next pointer and basic functions necessary to process the request, and then have each specific handler inherit the base handler class. This will ensure that each specific handler class has inherited the logic needed to call the next handler in the chain, and will result in the least amount of reused code. Second, the client must create and link the chain. This can either be done upfront before runtime, or dynamically as requests are either fulfilled or rejected. The end goal is to have the sent request pass through all handlers until the request is fulfilled, no matter the order. So it is important that each handler has a link to the next handler in the chain. If it doesn't have a link to the next handler in the chain, it is therefore the last handler in the chain, and must be able to exit without erroring. Finally, the client passes the request to the first handler in the chain, where it will flow down the chain until the request is fulfilled. This basic source code describes how we would get the current date in JavaScript using the chain of responsibility design pattern. Here we are using chain of responsibility to pass the request all the way down the chain, with each handler both adding the response to the message to the output and sending the message further down the chain. This is very similar to how a data logger would use chain of responsibility, as each successive handler will add their own information to the log if it is pertinent. As described earlier, we start by making an abstract handler class, which is kept brief here. This handler class contains a next pointer and a setter function, which allows us to set this pointer. Finally, it contains a process function, which our specific handlers will overwrite with their own versions based on how they process the request. We then extend the handler class to make 3 new classes: year handler, month handler, and day handler. Each of these classes retains the base class's setNext function for setting the next pointer and implements the process function. For example, the year handler function grabs the current date, and if it is not the last in the chain, returns it concatenated with a custom delimiter and the next handler's output. If it is the last in the chain, it simply returns the year. If we were to combine the previous code with this code snippet, which would be run by the client, we would log the current date, for example, 2/22/2022, to the console. As discussed in our implementation details, we now have to create and link the chain in the client, which can be seen here. We create a new instance of year handler, month handler, and day handler, and set the next pointer of our month handler instance to day handler, and the next pointer of our day handler instance to year handler. This ensures that our date will follow the month/day/year format. However, a different ordering, for example, the ISO time format, can easily be achieved by just switching around the next pointers of these objects. We then call the process function of the first object in the chain, monthHandler, with the slash as our delimiter. And here are our references.